Okay, so in this problem, in this video, we're going to learn how a dipole moves in a uniform electric field. Now, if you recall from a couple videos ago, a dipole essentially is two charges, positive and negative. Okay, but in this case, what we've done is we've connected them with by a very light rod. So the mass of the rod is unimportant, doesn't do anything, but we've connected them with a very light rod, and we're going to ask the question: what happens? How does this thing move in a uniform electric field? Okay, a bunch of things that we can do. Now, first of all, let's ask what would happen if the dipole was simply parallel to the electric field. Okay, if there was Q here and then minus Q here, okay, and the electric field was pointing in this direction. All right, now in this case, you see that what would happen is that the charge on the right hand side would experience a force to the right, and the one on the left is going to experience an equal and opposite force to the left, such that the net force on this system would be 0 and nothing would happen. It would simply stay at rest. Okay. However, if the dipole makes an angle theta with the electric field, some small angle, okay, and we're going to keep theta small, okay, such that sine of theta is approximately equal to theta. So that's what we're going to do. So when we do this, now what happens is that the one on the right experiences a force QE in this direction, the other one experiences a force QE in the opposite direction. Now, if you look at this picture, okay, what we have a torque about the center. Okay, so it's going to be pulled in this direction. It's going to start spinning. Okay, it's going to spin. It's going to spin all the way to the other end, and then it's going to spin back, because now when it is in this orientation right here, okay, what we know is that the force is once again going to try to pull it towards the equilibrium position, okay, which is the picture on the right. So this is the equilibrium position, and the forces on the left hand side are going to try to pull it towards this equilibrium position. So essentially what we have an oscillating object, okay, and we'll show that for small angles theta, the net the motion is going to end up being simple harmonic. Okay, so first let's figure out the resultant force, if you may. And what we know is that the F net, of course, in the problem is 0, but when the angle is theta, the restoring force, okay, the force that tries to bring it towards equilibrium, or that is going to end up being equal to let the masses be m. The force is going to be equal to restoring force is going to be equal to negative QE, okay, times L. So it will be negative QE times sine of theta, okay, but it's going to be twice this, because there are two of these that are trying to make it go right back towards the equilibrium. Now what we know is that this theta, okay, is small, so that we know that this is approximately equal to theta, and if, say, this were the arc length s at any point, then we know that it is equal to 2QE times s over the or rather s over the radius L. Okay, but that's the point about which it's going to spin. So now that we know this, we know that this 2QE s over L, okay, is equal to is the net force, and it's going to cause an acceleration towards the center, and that is going to be equal to m, or rather 2m, with both the masses are going to be accelerated, 2m times what's the thing? It's going to be a along the tangent. Okay, so this a tangential is going to be equal to negative QE over ml times s. This is nothing but our equation for a simple harmonic motion. So comparing with a equals negative omega square x. So now we can write down omega. So we know, first of all, motion is simple harmonic, say such m, with omega equals square root of QE over ml. Okay, and going to give us a time period is 2 pi square root ml over QE. Okay, so we showed that the motion is going to be simple harmonic by just looking at the forces, and then we found the time period for the motion.